Thank you.
Okay, so we're going to continue with our next talk. So our next talk is titled Salience Rank, Efficient Unsupervised Keyphrase Extraction with Topic Modeling. And the talk is given by Weiwei Chen. Thank you, Weiwei.
Hi, how are you? So my name is Weiwei Chen. I'm a machine learning scientist from Amazon Development Center, Germany. And today I'm going to talk about a new keyphrase extraction algorithm we developed. This is a joint work with Natalina Telema from the University of Chicago. She is an intern working with me last summer. So keyphrases should be familiar to most of the people here. When you're reading a scientific paper, often you see a set of keyphrases or say keywords provided on the title page, so people can have a quick idea about the paper without actually reading it. Keyphrases have commercial applications as well. For example, this is a website on TripAdvisor. On the hotel page of TripAdvisor, you see that keyphrase is extracted from reviews and put on the top of the hotel page. So customer can have a very quick idea about the key features of a hotel without actually reading through everything. Oh, by the way, this is a very good hotel next to our office in Berlin, just in case you visit. The goal of keyphrase extraction is to find a collection of phrases in a document that provide a concise summary of the content. So here, the input is a text document, and the output is a set, or say a ranking of phrases. To evaluate the output, what we typically do is to compare the phrases we extracted with the phrases provided by human annotator, using some measures such as position, recall, and F-scores. An automatic keyphrase extraction pipeline typically operates in two steps. So first, we're using some heuristics to select some candidates from the document. And then we're using machine learning tools to decide which of them are good keyphrases. In the first step, one of the widely used heuristic is to select noun phrases using part-of-speech tagging. For example, here, we select 0 or more adjectives with 1 or more nouns. Another widely used heuristic is to simply select phrases that don't contain some predefined stop words. For the second step, which is the focus of this talk, both supervised and unsupervised approach have been used. In the supervised case, the question if a candidate is a good keyphrase can be cast as a binary classification problem. There are also efforts on pairwise ranking, and the idea is to learn a model to compare two candidates, and then finally, the ranking of keyphrases can be obtained by aggregating all these pairwise comparisons. Our approach is an unsupervised approach. There are different types of unsupervised approach, and here is a short list of them. Our approach can be considered as a mix of graph-based and topic-based approach, which I will talk a little bit more in the following. In a graph-based approach, the intuition is that a candidate phrase is important if it is related to other candidates, which in turn are also important. So this is a typical procedure. First we build a word graph from the input document, where in the graph, each node represents a word in the document, and the edges indicate the relatedness between two words. Then we perform random work on this word graph to obtain the word scores. So here, PageRank is arguably the most famous example. Finally, we select the key phrases with this word score obtained from the random walk. Our approach is closely related to topical PageRank, which is considered as a state of art in this line of research. The key idea in topical PageRank is to use the topical information induced from LDA to guide the random walk. For the people who don't know LDA, so LDA is a topic modeling algorithm where a topic in LDA is a distribution over the vocabulary. For example, here, the topic K, the word director and Oscar have very high probability. which suggests this is a topic talk a lot about movies. And each document in LDA is viewed as a mixture of topics. And for example, here, this document D talks a lot about topic 2 and 3, but not so much about others. Given a collection of documents, LDA is able to discover such topical information for the documents. So here is how topical PageRank works. Giving a word graph where nodes represent word in a document, and the edges indicate the relatedness between words, using, for example, co-occurrence statistics. The score of each word under topic T is determined by the following random walk. For the people who are familiar with the PageRank, this is very similar to PageRank, except that instead of using a uniform jump probability, here the jump probability is set to PT given WI. So intuitively, this indicates how much a word WI focuses on topic T. Now we run this random walk. After the random walk is converged, for topic T, we obtain a topic-specific Keyphrase score by summing up all these word scores. And finally, we obtain the final Keyphrase score by aggregate all these K-scores from the K-topics. And put everything graphically, this is what topic PageRank does. It first constructs a word graph using the co-occurrence statistics, and then we run LDA to estimate the K-latent topics. Then we run PageRank K times, once per each topic, to obtain topic-specific Keyphrase scores. And finally, all these scores are aggregated, we get the overall Keyphrase scores. Our contribution, Salience rank, improves the topic PageRank and makes two notable contributions. The first, while we're still exploiting the topic information extracted by LDA, we run PageRank only once instead of K times. We achieve that without sacrificing the face quality. And in fact, sometimes we even improve the face quality. The second contribution is configurability. With the Salience rank, users are able to balance between topic and corpus specificity of the extracted keyphrases and can turn the result based on their particular use cases. So here is an intuition. On one hand, we want to have keyphrases that are relevant to specific topics. But on the other hand, we also want the keyphrases as a whole have a very good coverage of all the major topics in the documents. So put it differently, sometimes keyphrases are representative exclusively for certain topics are more appropriate, while other times the keyphrases that are representative of the corpus as a whole are more appropriate. It is, therefore, useful to have a keyphrase extraction algorithm to have an internal switch controlling the extent to which our results skew towards specific topics, or conversely, the extent to which they generalize across all the topics. To achieve that, let's first quantitatively define what is topics and corpus specificity. We define the topic specificity of a word as the KL divergence from PT given W to PT. And intuitively, this measures how much a word is shared across different topics. So here is a toy example. Suppose we have two topics, which are equally likely. We see here, because the first word, W1, is mainly focused on one topic, the TS of W1 is very high. But on the other hand, the TS of W3 is 0 because PT given W3 are equally shared between the two topics. Right? So this is what it looks like graphically. So if the word is less shared between the two topics, the TS is very high. You see that this behavior satisfies our purpose for topic specificity. So for corpus specificity, we use a very direct definition to define it as the word frequency in the corpus. So I have to note here that what is important is to distinguish topics and corpus specificity. And here is just one way to defining them. With these two concepts defined, we can define the saliency of a word as a linear combination between these two concepts. Here, the alpha is a trade-off parameter balancing these two concepts. Now, again, the CS, corpus specificity, is high if the word occurs often in general, while the TS is high if the word is less shared across topics. So with the word salience, we define our random walk in the following way, where we set the jump probability using the word salience. So here, all the topical information is included in the S of WI. And we compare with TPR, we only need to run page rank once instead of K times. So here are some empirical results. 500 News and InSpec are two widely used Keyphrase extraction benchmark data. 500 News is a collection of news articles where the keyphrase is obtained through mechanical Turk. InSpec is a collection of a paper abstract of a computer science journal where the keyphrases are provided by the authors. Here, the key information, the key takeaway message is that in terms of performance, our proposal, Salience rank, obtain at least comparable keyphrases in terms of quality while computationally more efficient. In terms of configurability, here with the 500 News, we show that the trade-off between topic and corpus specificity indeed has a considerable impact on the performance. Besides this quantitative analysis, we also have a qualitative example. So here is an example on the InSpec abstract. So what we observe is that when we set the CS high, the corpus specificity high, we tend to get key phrases that are rather generic. So it is arguably better if it's presented to people who are outside the area of the journal. On the other hand, if we set the topic specificity very high, we tend to get key phrases that are rather specific. Those are arguably better for the experts. So to conclude, we proposed a new unsupervised keyphrase extraction algorithm. Compared with the state of art, it produced at least comparable keyphrases in terms of quality while being computationally more efficient. And it is also highly configurable because user can turn the topic and the corpus specificity depending on their use cases. So we see a number of applications of keyphrase retraction at Amazon. For example, at the front end, similar to the use case of a trade advisor, we can provide a quick summary of the product so people can know about the product very quickly. And we can also use keyphrases to help people finding what they're looking for quicker. There are also a number of applications on the back end as well. For example, we can use keyphrases as index terms in search. Most of our search are based on the product information provided by vendors and sellers. With keyphrases extracted from customer reviews, we can improve search by considering what the customers are telling us. So these are all from my side. I'm happy to answer your questions. Thanks.
Okay, and we have, I think, a few minutes for questions. Please step up to the mic if you have a question.
Have you made your work available as a package? Is it consumable, or is it only published?
Oh yeah, right. So we plan to put it on the code base very soon. So far it's not, but we plan to do that. Yeah.
Ted?
Hi. It wasn't clear to me when you did the random jump to a different topic, right? You had with probability 1 minus lambda, you jump to. So where is topic T a node in the graph, or how do you jump to topic T? I know what it means to jump to a random node in the graph, but yeah.
Yeah, thank you for asking that. Let me go back to the slides. For the topical page rank, so they do the random work once per each topic. So in a sense that the jump is really just, we don't really jump between topics, but rather we perform one random work on each topic. So does this answer the question?
I guess, do you then segment words into topics?
No, so then basically, we don't really need to segment it because that for one particular topic, now we have this word graph, and the word graph is basically weighted. It's basically weighted according to that particular topic, the information from that particular topic. Right? So that is why we jump. And just one comment on this lambda. So this is also a parameter you can set up for the random work. And typically in PageRank it's set up to 85%, but this is something you can also play with. Thanks.
Number 4.
Hi, I had a question about how your keyword search handles synonyms, maybe that aren't present necessarily in the topic body of work. So.
Thank you for the question. So in this line of work, there depends on what kind of application you make. And in this particular line of work, that we assume that the key phrases you extracted are exactly what you can find from the document. So you don't really go beyond what you can see from the document. But in the keyphrase extraction literature, there are approaches using external resources to basically expand your search space. For example, you can think of using WordNet, where you can find synonyms and other related words. But in this particular work, we don't really consider that. But of course, you can extend to that. Thanks.
Number 3.
Hi, interesting work.
Hi.
So I happen to work on the same problem, and from last year's EM and LP, there was actually some work on this, which is based on graph degeneracy methods, and they actually experimented on inspect as well, and they reported performance that's more than doubled yours. So is there any reason to stick with the current PageRank framework or topical ranking methods for keyphrase extraction, or should we do a paradigm shift here?
Oh yeah, so this is actually, I think it's a bigger question than what you were suggesting. First of all, the first question is that you have a problem with keyphrase extraction, right? So you want to solve it. Should you do it a supervised way or should you do it unsupervised way? Now, a lot of settings you can decide. In this case, we don't really have particularly human annotated data. So to start with, we start with an unsupervised approach. Right? And in case if you have an application where you indeed already have this annotated data, and also annotation cost is not an issue for you, then of course you can go to the supervised case. And generally, the supervised approach have a better performance compared with unsupervised case. I don't know if this answers your question.
For the record, their method is actually graph-based and
I
unsupervised.
see. Do you know the exact name of their approach? The reason is the following. The reason I'm saying is the following: that in the paper, we compare to more methods than just TBR, and the basic result change a lot. Depends how do you change other settings before you actually do the random work. Think about it. So here in this particular work, I select the candidate using the part of speed tagging heuristic. But if you change to another way to select you candidates, they can dramatically change the results. Also, how do you construct a graph can also change a lot. Here, the key message is to make a very fair comparison between topic and page rank, so we set every exact setting the same. Right? Of course, if you turn the setting a little bit, you can also get a better result. Moreover, here the trade-off parameter I show have played an important role, depends on your data set. We actually don't turn that, because for a fair comparison, we actually fix that parameter to just make the comparison more fair across board. Does that make sense?
Sure. Well, still, you didn't address, since both methods are unsupervised, though, what are the reasons that people should choose this method over, the graph degeneracy-based methods?
I couldn't really answer that before I have a direct comparison between that method.
Sure. Let's talk more in the poster.
Yeah, I take it offline. We're out of time, so let's thank Wei Wei again. Thank you very much.
Thank you.